In this video lecture, we'll discuss the methods of carrier regeneration using PLL at the receiver. So we'll have a look at the methods which are used for carrier regeneration using PLL circuit at the receiver, which is obviously required for the coherent type of demodulation process. So basically there are two major methods that are being used that incorporate PLL loop for the carrier regeneration process. The first one is your squaring loop, signal squaring loop. Second one is the Costas loop. So these are the two methods which make use of PLL at the receiver to regenerate the carrier signal. So we'll have a look at both these methods one by one. First we'll begin with the signal squaring loop. So I'll first draw the block diagram for this method, and then I'll discuss it in detail. So these are the four different blocks that are being used in the case of signal squaring loop. So the incoming signal is your, let's say, DSB-SC sinusoid, double sideband suppressed carrier sinusoid, that is MT multiplied by cos omega CT. MT is your baseband signal and cos omega CT is your carrier signal. So MT cos omega CT will be your double sideband suppressed carrier sinusoid, right? We are giving this signal as input to this squaring loop. So the first step is we square the input signal, and then it is passed through a band pass filter which is centered around the frequency that is twice of omega c, and then we further pass it through a PLL circuit, and then further the frequency divider. Okay, so let us analyze this whole process mathematically, how this loop helps us to regenerate back the carrier signal. The very first step is the squaring process. So the output of this squaring process is x of t. So this x of t will be nothing but square of the input signal. Square of the input signal, that is mt into cos omega ct, square of this, right? Let us simplify it. We get 1 by 2 m squared t plus 1 by 2 m squared t cos of 2 omega ct, right? Now this m square t, this is a non-negative signal. Obviously this is a non-negative signal, and therefore it has non-zero average value. We can say that it's a non-negative signal, hence it has non-zero average value, in contrast to mt, which has a zero average value. This m square t will have a non-zero average value since it is a non-negative signal. So let the average value, which is the DC component of this m square by 2, be, let's say, some constant k. Average value, which is the DC component, let it be k. So we can express this m square t by 2 as k plus some phi of t, isn't it? Where phi of t is the zero mean baseband signal. This phi of t is nothing but your zero mean, it's nothing but your zero mean baseband signal. So thus we can say that this x of t is nothing but half of m squared t plus k times, just a second, plus k times cos 2 omega ct plus phi t into cos of 2 omega ct, isn't it? So now this xt is further passed through a band pass filter which is centered around frequency plus minus 2 omega c. So this band pass filter will completely suppress this signal first of all, okay, because it has frequency omega m, which is the baseband frequency. So twice of omega m, which is the baseband frequency, and the spectrum is centered around omega is equal to 0. So this will be completely suppressed, and it will also suppress most of this signal phi t. Most of this will be suppressed. Now I am saying most of the signal will be suppressed because this phi t has 0 DC value. This phi t in particular has 0 DC value, right? And moreover, this component is distributed over a band of 4 B hertz, we can say, because obviously the frequency here is twice of omega c. It is centered around omega c, but the power at twice of omega c is 0 or equivalent to 0. If we talk about this signal as a whole, it is centered around twice of omega c, but the power at twice of omega c is almost 0, approximately equal to 0, right? This is because this component is distributed over a band of 4 B hertz, which is centered at twice of omega c, because this phi t has 0 DC value, right? Hence a very little part of this signal, a very little part of this will be passed through the band pass filter, and most of it will be suppressed. And the third component is this component that is some constant k multiplied by cos 2 omega ct, which is centered around twice of omega c, and all the impulses are located at this frequency only, twice of omega c, plus minus twice of omega c. So this component will be completely passed, and a very small undesired part of this component will be passed, okay. That means all the power concentrated at twice of omega c will be passed. So this will be totally passed, and a very undesired and small quantity of this third component will also be passed, right? And this undesired residue of this will be tracked by the cleaned up by the PLL signal rather, okay, because this xt signal, if you look at the block diagram, is further after passing through band pass filter, it is passed through a PLL. Okay, the purpose of PLL is to track the frequency. So this is one of the major component. It will track its frequency, that is twice of omega c, and it will clean up this undesired part. Okay, so once we pass it through PLL, we pass this entire signal through PLL. So the resultant will be, you can say, signal with frequency twice of omega c, and it cleans or eliminates the undesired components, which is the slight portion of the third component, right? And now this PLL output is further passed through your frequency divider circuit, and that will divide the frequency of the input signal by 2. We are using a 2:1 frequency divider circuit, and the resultant will be the signal cos omega ct, k times cos omega ct, which is nothing but your regenerated carrier signal. So this is how we make use of this signal squaring loop method to regenerate back your carrier signal. So this is your first type of carrier acquisition method, signal squaring loop, which makes use of PLL to regenerate back your carrier signal. Moving on to the second type of the carrier acquisition method, that is the Costas loop method. I'll first draw the block diagram of it and then we'll have a discussion over it. So again, let us take the same input signal, that is the double sideband suppressed carrier signal, that is your MT multiplied by cos omega CT plus theta I. Theta is the input phase. And we divide the signal in two branches. Rather, we broadcast the signal in two branches of the PLL. And we have a low pass filter here, second low pass filter here, and again a low pass filter which is narrow band. And this gives the input to the VCO, voltage controlled oscillator, and one of the input is given to the upper branch and the other with the phase shift of pi by 2 is given to the lower branch. Alright, so the signal over here is MT into cos omega C T plus theta naught, and signal here is MT sine, signal here is not MT, it's rather twice of cos of omega CT plus theta naught, and signal here is twice of sine of omega CT plus theta naught. Okay, and signals from the low pass filter, which is nothing but your MT cos theta E, which is the phase error, and here MT into sine of theta E, which is again the phase error. This is the output and given into a multiplier, and this which is nothing but this multiplied output will be 1 by 2 m squared t into sine 2 theta E, right? So this is the block diagram for the Costas loop. If we carefully analyze this block diagram, we find that there are two branches, and if we again look at these two branches, these are your two PLLs, okay, with the carrier of phase shift of pi by 2. These are two PLL used in the two different branches and the feedback system. So we can say that the incoming signal is your again DSB-SC signal, that is MT into cos omega CT plus theta I. So at the receiver, VCO generates a carrier signal. At VCO, the carrier signal generated is cos omega CT plus theta naught. Okay, the phase error is theta E is equal to theta I minus theta naught. So all these signals are indicated in this block diagram. The two low pass filters, these two low pass filters, they suppresses the high frequency terms to yield these two low pass filter, they suppresses the high frequency terms to yield your MT into cos theta E and MT into sine theta E. Theta E, right? And these outputs are further multiplied. These two are then multiplied to give your MT square into sine 2 theta E. When this is passed through this MT square sine 2 theta E, you can see that this is passed through the low pass filter, through a narrow band low pass filter rather. When this is passed through a narrow band low pass filter, the output is R into sine 2 theta E, right? Where R is the DC component of M square. This R in particular is the DC component of M squared T by 2. So this signal R into sine 2 theta is further applied to the input to the VCO. You can clearly see it is applied this output from low pass filter is applied to the input of the VCO with free running frequency omega c, right? So the input R sine 2 theta E, this increases the output frequency, which in turn reduces theta E. So the purpose is this is applied to input to a VCO whose free running frequency is omega c. So so when we apply this input R sine 2 theta E, which is kind of a feedback signal to this VCO with free running frequency omega c, the input it will increase the output frequency. It will increase the output frequency, which in turn reduces theta E, which is the basic principle of PLL. So this is kind of a feedback signal that will adjust the output frequency of VCO such that the phase error is minimized and this loop is locked in terms of the frequency as well as in terms of the phase. So this is the second method of the carrier regeneration, or you can say carrier acquisition, which is your Costas loop. So basically these two methods, Costas loop and the squaring loop methods, are used for the carrier regeneration process, which is quite important for the coherent demodulation, which requires a synchronized regenerated carrier at the receiver end. That is the integral part of all the communication receiver. All the communication receiver has to have the carrier regeneration process for the coherent demodulation process, right? And this was the example that we analyzed for, you can say, a double sideband signal for both the cases, for both the methods, signal squaring loop as well as Costas loop. We analyzed it for the double sideband suppressed carrier signals. These two methods are also applicable for the other kind of modulated signals like SSB-SC, which is the single sideband suppressed carrier. We can apply the similar kind of the processes, the mathematical and analytical steps for the other modulated signals as well, to analyze these two carrier regeneration methods. Okay, thank you. That's all for this video lecture.